Hi, welcome to Ethereal Mechanics Foundation Series video number 3. In this video, we're going to perform the disambiguation of all the models for the loop experiments that we found. And we're also going to release a new electromagnetism model of light. Well, we're not going to release it. We're going to point it out to you. It's been there in front of you, in front of your face all the time. So, in the previous videos, resulted in a 4-way tie for the model of self-inducting loops, closed loops. And we're going to review that. Here in this video, we're going to disambiguate the results, leaving only one. The surviving model will then be discussed with regard to the phenomenon of light, where the new electromagnetism model for light will be discussed for the first time in 20 years. And some of my followers may have wondered why I did not release a new electromagnetism model for light 20 years ago. And in fact, I did release it. I just never brought attention to it. My intent was to hide it in plain sight. And let me give you the reason for and the method to my madness. Because like an old gold rush, the minute you tell people you've struck gold, you'll be inundated with claim jumpers and plagiarizers and all that stuff. Philo T. Farnsworth invented TV. There's two different stories on what happened. You look it up, but the same idea. He basically lost it because he explained what he did to people, and people just praised it. Same with the Wright brothers. Their patents basically made public how they did it. And they spent all their time in court trying to protect their patents from infringers when, in fact, the rest of the world was working around them, and their airplanes became obsolete too quick. Same with Tesla. He showed everybody how to do it, and everybody was working. He had thousands of people, engineers, millions of engineers working around him. He couldn't keep ahead of the pack of a million engineers working around you. And so he had to go off and do really crazy stuff that really didn't amount to much because he had to really stretch. So my idea was to tell the truth and hope that the false prior knowledge and belief instilled by classical training would protect me from potential plagiarists. And I think it's worked. Because when I tell people, in the beginning I told, oh, there's no wave model. Which is true. And we'll explain that later on in the video. Who in their right mind would plagiarize new models of electromagnetism if it has no wave model? And that's the problem, because you don't need a wave model. I'm going to show you that the model for light has been there. It's been there all the time. And that a wave model is not appropriate. And we'll get into all that. But it's been there. I have just not pointed it out. So what I'm going to do is the video, I'm going to connect the dots for you. So here's how this video is going to play out. First we're going to do the disambiguation. And then we're going to do the technique for disambiguating the correct model should clue you into what the new electromagnetism model for light is. Let's see if you can figure it out. After the disambiguation, I'll connect the dots for those people who didn't get it. And then together today we'll drive the final stake into the heart of Maxwell's plane wave derivation. And in the following videos we're going to take new electromagnetism down the rabbit hole to reveal the wonders that have been hidden in plain sight. Some of the wonders. We need Ethereal Mechanics to go get the rest of them. So what are we left? After all the other experiment videos that we've done, and this is just for closed loop inductors, okay, we did the research for the quad loop experiment, and we found from classical theory there are only two models that can actually give reasonable results. Jackson is a bogus derivation because he includes internal inductance, which I've shown in the earlier videos is a completely fraudulent derivation. However, if you remove the intrinsic inductance from his result, he gets very good results. Okay, so this is removing, and you can see the results are pretty much equal across the board. Okay, Maxwell mutual induction is also a fraud because it's not a self-inducting loop. It's simply if you take a loop of wire, and I'm showing the loop, half the loop there, okay, and if you put one filamentary wire at the center of the wire, and one filamentary loop at the outside of the radius of the wire. So if I blow it up over here, one wire here, the source filament here, the target filament here at the radius of the diameter of the radius of the wire, going around the loop, and then compute the mutual inductance between those two loops of wire, you're going to get an excellent value for the self-inductance of wire. But that's completely fraudulent because that's not how the currents move in a real loop of wire. But it's amazing in nature how you can have totally bogus models. It can give you really good answers. I mean, this is an excellent example of that there more than one model will exist. Rule of acquisition 11. Expect more than one. And then from the Rhombus experiment, we found 2 point charge models that also fit the data. And what I did here is I took the point charge models and made them work for a solid inductor and then computed what the quad loop results should be from the results that came out of the Rhombus experiment. And as you can see, all of these models give very, 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 very good answers. Well within the ability of the precision inductance meter to measure them. Okay, so the question is, which one is right? I mean, now that we have 4, we have to disambiguate. Which is the one? We have to find other experiments now where one of these will give the right answers and the others will not. That's how we disambiguate, when we have more than one model that fits. And I'm not going to read, this is Rule of Acquisition 11, which this is a perfect example for. You can read those on your own. I'm not going to read those for you. So what we're going to use, we need Rule of Acquisition number 2, where a single wrong answer can prove a theory wrong. We need to find observation X, which will prove one of the models over all the others. So the objective, remember, is to find a model for inductance that works as well among point charges as it does for closed loops. So far, all experiments have been done with closed loops, whether they be circles or rhombuses. Now, classical theory automatically eliminates itself. By their own rules, it's forbidden for one electron to inductively couple to another electron unless they're part of a closed loop. And I'm going to reiterate from the textbook, from electromagnetic engineering. I actually took this quote from the 4th edition, but I'm sure it's somewhere in the 7th edition. The equation for vector magnetic potentials may be written in differential form if we again agree not to attribute any physical significance to the result until the entire closed path in which the current flows is considered. So it's meaningless unless you have a closed path. So I guess electrons are supposed to ignore the magnetic field changes unless they're in a closed loop. How ridiculous is that? So we can automatically remove classical results. So that leaves just the 2 point charge forms that were found in the Rhombus experiment. So now, because these all work for closed loop, we need to find that observation X. Okay, this observation here is going to be an open loop experiment. Okay, and what the experiment we're going to do is a coupling pattern from one dipole antenna to another. These results are well known. I don't have to run the experiments. They're all over the internet. And so a classically trained person will say, well, wait a minute, hold on. This situation is different because this requires a wave equation. Well, I want you to watch and unlearn. Case 1. The electromagnetic coupling between 2 separate loops of wires completely described without a wave model. If one were also to account for the electromagnetic wave propagation from loop A to B, you would oversubscribe the effects you've already measured just by measuring this experiment. And the mutual induction experiment is well known, and the results are well known. They're easy to measure. And you can get good answers just with Faraday's law or any of these models all by itself. If now you say, well, now there's this other effect, this electromagnetic wave propagation, well, then you're going to get a different answer because we get very, very good answers with just this, which means these include all the effects because they were measured. So you can't say there's another effect here. Let me give you case number 2. Remember, we used the Rhombus experiment. And in the Rhombus experiment, we have to compute or determine the effects from each filamentary fragment to the other filamentary fragment across the distance of space. And to say now, well, okay, if I break these 2 halves of the rhombus apart, then somehow there's another mode of coupling from that fragment to the other that isn't accounted for with this measurement? That's completely ridiculous. That's fantasy land. And therefore, when we're measuring induction in loops of wire, if we're not measuring all the effects, and there's this other effect called a wave propagation between them that we're not accounting for, then how is that missing from our measurements? This measurement we make has to be all-inclusive of everything that it goes on when fragment A couples to fragment B. And it doesn't matter if the loops are closed or separated by a distance or separated by 1,000,000 miles. You can't say to me just because this loop is now not connected, the 2 halves are not connected, that now there exists another mode of propagation from this side of the loop to the other. That's fantasy land. Okay, if there were additional wave model, we'd be doubly accounting for effects that have already been measured. Again, by their own admission, there is no way, this is for classical theory, there is no way that a changing magnetic field can couple energy to an open loop, a dipole, even to a point charge, according to classical theory. Okay? And therefore, there's no way that they can claim that Maxwell's electromagnetic wave propagation works, because if there's a magnetic field component to it, there's no way a magnetic field can couple to an open loop and give energy. So that's more indication that their plane wave derivation is complete bunk, because they have not explained how a magnetic field can couple to an open loop. And so their whole and to say that, well, gee, there's more effects here when the loop opens, and that's why Maxwell needed his plane wave derivation, says they've oversubscribed the effects. And that's why I showed you in the other derivations that Maxwell's plane wave derivation leads to over unity. They've oversubscribed the effects. And I think I'm beating a dead horse. You kind of get it. If the measurement we made doesn't include all the effects, then something is wrong in the world of physics. And therefore, by adding a plane wave equation on top of that, it's just going to oversubscribe what's already been measured. All right, so let's go back. We're just going to use the 2 point charge forms that we found from the Rhombus experiment. We're turning them on their sides now. Okay, here's the spherical field, and here's the longitudinal field, because we're going to do dipoles in this fashion, vertically oriented on the piece of paper. Okay, so the longitudinal field now will be, it's longitudinal to the direction of charge accelerator. It's going to look like this. So the simulation, I'm not going to go into too much detail here. This is for you to read on your own in case you want to try to simulate this on your own. I'm showing you what I did for the computer simulation. I'm doing all the lengths are in lambda, wavelengths. The distance between the source and the target dipole is 1,000 lambda. And the length of the dipoles are half lambda. I've broken up the dipoles into 30 fragments, where the length of the dipole is 30 times the delta L, the fragment length. Okay, now what you got to do is, in the source, I'm assuming a standing wave, a current standing wave, where the current goes this way, and the amplitude is 1 at the center of the dipole and 0 at the ends. And it follows a cosine distribution. You compute the distance from each source fragment to each target fragment. Okay, and then you compute the distance from the target fragment to the center to get the total distance traveled. Compute the distance in wavelengths from here down to the center. That's total distance t. Multiply it by 2 pi, take the cosine and multiply it by the amplitude of this fragment here. And then just sum that up. And then move this dipole, target dipole, around in a complete circle around the source dipole. And there's 2 modes, 2 scenarios. One where we keep the target dipole parallel all the way around as we move it around. The other one is we're going to make sure that the target faces the source as it moves around the circle. So the first result is where the targets remain parallel. Okay, in other words, the source dipole is here, the target dipole is going to be here and then moved around, but kept parallel as it moves. And you can see 5008 gives a very good dipole pattern, whereas 5079 shows no energy is coupled across the broadside. Because if you take the amplitude, the way you read this is, this amplitude plot is the amplitude in this direction. That's the amplitude of 5079, and that's the amplitude of 5008. So in other words, we're plotting the amplitude as it goes around, as a radial distance from the center. So the farther a point is from the center, the more amplitude is in that direction. In this case here, 5079 shows absolutely 0 energy off the broadside of an antenna, and that is completely wrong. This is the energy you get if you keep your dipole parallel. If you keep your dipole facing, you get the classic dipole pattern, which every antenna engineer should know. And here's 5079, this is little red dot. It's completely 0 all the way around. So the winner, my friend, is 5008. It gives a proper dipole pattern. And now that's the model that we're going to use for induction until somebody, hopefully myself, finds something better. And with Ethereal Mechanics, I'm hoping to find something better. So if you did not connect the dots, because new induction accurately predicts the dipole radiation pattern, then it is the new electromagnetism model of light. In other words, induction encompasses everything needed for light except the wave model. And people might be saying, well, wait a minute, hold on. How come you don't have a wave model? Well, that's because all of the models, including classical theory and new electromagnetism, are measurements from a source to a target. All we're measuring is the end-to-end effects. We're not considering anything in between. It's a little bit ludicrous to try to infer what happens in between with what you only know from the ends. And that's the purpose of the new wave theories, to actually look at light and infer from its behavior what's going on in between. And that's why these models, whether it's classical theory or new induction and all that, even though they are the effects of light in measurement form, they do not explain how light travels from point A to point B. All they tell you is, if you make an electron wiggle this way over here, you're going to feel an effect over here. It doesn't explain how it gets from point A to B. Neither does classical theory. And that's why Maxwell's plane wave derivation is complete and utter fantasy. Okay? We can't do it from this. We need to infer other things, and that's the reason for the new wave theory. Okay. And also, if you don't believe that this is the model for light, consider this. For my graduate thesis, I wanted to very accurately compute the inductances of real inductors. This is a single-sided printed circuit board with multiple inductors inscribed on it. And what I wanted to do is calculate, well, what happens to the inductance of an inductor when it's sandwiched between two conducting planes. Like, you get ground planes in printed circuit boards. So, because this is installative, I just put this inductor over another copper-clad PC board to represent a ground plane below. This is a single-sided PC board here, and I made it on top. So now, and I put a weight on it to kind of squash the two together. So now I have a ground plane that's 1/16 of an inch on either side of a inductor I want to test. Now, how does that affect the inductance? Well, what I did is I assumed, well, I knew back in my graduate thesis that this was the model of light. Couldn't say that because that would have been too much for the people that supported me to accept. And so what I just said is, well, I'm going to treat it like a method of images, which is in the other textbook for electrostatics. Whereas each one of those ground planes is like a mirror. And the inductor in between is like the candle between two mirrors, and the images go off to infinity. Now, granted, the images get darker and darker and darker the farther away they get, because mirrors aren't perfectly 100% reflecting. So I did the same thing. I modeled my inductors, and then I took the computer and I made copies of that inductor going out to infinity. And because the way things reflect off conductors, they reflect as negatives, these would be negative, these would be positive, negative, positive, negative, positive, negative. Same down here. And as you go farther and farther away, it's 0.97% reflect efficiency, 97 squared, 0.97 cubed, all the way down. So the efficiency, the reflectivity goes down and down. They become darker and darker. And so I did the computer model, and I did the computer model to say, well, okay, let's just keep adding pairs and see what the effect is. And I just kept adding pairs. This is every pair. So this would be the first pair, the second pair, yada, yada, yada. And as you can see, as the farther the number of pairs I add up going out to infinity converge to a really nice number. And the computed for this experiment here is about 115. The measured is about 112, which is very, very good. Other ones came even closer. And that's pretty good, because my ability to measure isn't that good with the Agilent LCR meter. 2% measurement is well within the ability, is well within the precision of the instrument. The instrument's probably around 3%. And then you also have it's hard when you're just laying things on top of each other. You don't know if the per distance is perfectly 1/16 of an inch, and there's a whole bunch of other variables. So to get only 2% difference at the worst case here is really, really good. So if it quacks like a duck, if by treating the emissions of inductors if it were light, I was able to obtain fantastically good answers to the problem of single and dual ground plane reflections. In my thesis research, I could only find limited prior art for single ground planes. In my opinion, it was very poor work, and nothing for dual. My friends, new electromagnetism is the only game in town. And finally, the power for light and radio waves diminishes by the inverse square of the distance. If we take the other electromagnetic models, they're all their inverse square at the force level. Okay, but the power is effectively the square of this. And so both electricity and magnetism, I'm just showing electricity here to represent the two, their power rolls off by a square of by the fourth of the distance. New induction, because it's only an inverse equation, when you take the power rolls off by an inverse square. And therefore, more again, if it quacks like a duck, if induction rolls off with the same amplitude that light from two distant antennas, or target and receiver roll off, then like I said, if it quacks like a duck. Again, I already explained this, why there's no wave equation, because we're trying to, these measurements only measure the source to the target with all the complicated effects in between wrapped up into one measurement. It doesn't explain how the energy is emitted from the source into the medium, how the medium travels the energy, or how that energy that when it hits the target couples to the target. All of those effects are wrapped up into one single measurement. And trying to infer what's going on there just from the endpoints is very problematic. And therefore, new electromagnetism is basically an empirical measurement which mimics what we see happening. And we have to infer the rest, and that's the reason for the new wave model. And that's Ethereal Mechanics, and the new wave model is an attempt to explain what happens. So let's go to the tearing ceremony, my friends. So we basically tore Maxwell's equation, the final new butthole, because it's already oversubscribing what is already measured between fragments of a loop of wire. And we're leaving chapter 11 aligned, because transmission lines are not really field. They're just, lumped parameter circuit models. So there's nothing wrong with these. These work pretty good. And these are only approximations. Everybody knows that. So I'm leaving chapter 11 alone. But chapter 12 is the uniform plane wave, baloney, unicorn stuff. And this gets into guided wave models. And we're going to get into that with ethereal mechanics and show you better models later. So, goodbye. 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 And so we're pretty much at the appendices, and this is what's left of a modern textbook when you get rid of the garbage. And this inspired two rules of acquisition. I'm going to do a full video release on this. You can read this on your own. I'm having trouble naming this one. I'm trying to still come up with, but I don't really like this name because the name doesn't describe what it means. I like having names for the rules of acquisition that describe what they mean, so I'm not really happy with the Distinti uncertainty principle. And rule of acquisition 12, this is turning out to be a 12-part rule of acquisition. This will be released sometime in the next couple of weeks. These are just different parts of it. You can read that on your own. So in the next Foundation Series video, in this one we covered light. Next one we're going to cover inertia. The next one after that we're going to cover gravity. And tonight I'm going to give you a secret homework problem which is going to reveal another secret of electromagnetism I've been holding on to. Here's the homework problem. And we're going to reveal this. This is emf005. This is 006. One of these. Or maybe this is 4 and this is 5. It'll be not this one, but the next one we're going to reveal the homework. So, and you might have to look at the next video to get help with this to kind of explain what's going on. That's why I'm not putting the answer until the one after. So what I want you to do is we have a target charge over here separated from this system here. This system is a system of like charges that spin around themselves at the speed of light. Their tangential velocity is the speed of light. The radius that they spin around is r, or rp, and the distance from the radius of rotation to the target charge is d. This does not require any calculus, only algebra and a little geometry. So using new induction, derive the effect on the target charge due to the source charges for d much, much, much greater than r. Use c for the tangential speed, use q for all charges. Don't substitute numbers, keep in equation form. And here's your question. What does the resulting derivation look like? This will be revealed in 2 videos, which I think is going to be the conclusion, but in 2 videos. So there's your homework. It'll reveal to you an interesting secret that I've been holding on to. Thank you. Thank you for the donations that have been coming in. If you want to donate, go to my website. My website's woefully out of date, and there's a donate button there. I have fun with physicists because every time I show them stuff, they dismiss me out of hand without even seeing what I have. So I've given up on physicists. So thank you very much.